Now we return to the problem at hand, which is finding the distance ratio between the Small Magellanic Cloud and Delta Cephei. There is two parts to this problem. The first part, part A, asks us to find the ratio of the peak brightness of Delta Cephei to a corresponding hypothetical star in the Small Magellanic Cloud that is exactly like Delta Cephei, just located there. And we're going to have to make it clear which star is star 1 and star 2 when we use our formula. And we're going to have to remember that Delta Cephei is much brighter than its counterpart in the Small Magellanic Cloud. Okay, going back to Levet's graphs right here, we can see below here it says that the pulsation period of Delta Cephei is 5.4 days, and it has a peak visual magnitude of 3.48. So, of these two things, which one would be the same if Delta Cephei were in the Small Magellanic Cloud rather than where it is? Well, since time spans don't change with distance, the time it takes for light to get from one place to another will be different, but the actual time between spans will be the same. So it'll appear to rise and fall at a rate of 5.4 days. In other words, get brighter and dimmer with a rate of 5.4 days. Its magnitude, on the other hand, will be totally different, because if it were way out there in the Small Magellanic Cloud, it would be much dimmer than it is now. In fact, there's no way you could see with the naked eye, but you could see this with your naked eye on a dark night. So, therefore, we're going to look back at Levet's plots of the other Cephei variable stars in the Small Magellanic Clouds, the ones that are otherwise just like it. And we're going to say, okay, let's take our 5.4 days and let's figure out what would the magnitude be if it were in the Small Magellanic Cloud. So to begin, if we look at the left-hand plot, this right here is 10 days. Right there is 0 days, and that's 20. So 5 is about in the middle. So a wee bit closer, but not much. There we go. Yeah, looks pretty good. So, to the best that we can see, that's probably about 5.4, because remember that's 0 and that's 10. And I drew a straight line with my ruler. And if you look right there, it's crossing that curve. And if we look closely to where it's crossing the curve with the ruler, it's right around here. That looks about right. So you can see that the magnitude it would be somewhere between 14 and 15. And this is 14, and that's 14 and a half. So it's probably about 14 and a quarter, maybe a little more, maybe 14.3. Okay, but she also made a similar plot over here, and this might be better, because you can see how all these points in the linear plot on a linear scale came out over here to get all spread out, and those on the magnitude scale on this axis become looking like a line. So, well, now where do we mark it? What do these numbers represent? Oh yeah, those numbers, remember, represented log of the period in days. So that period was 5.4 days. So if I take my calculator and I type in 5.4, and then I hit the log button, that is the logarithm of 5.4. So that's 0.733, something like that. Or 7324, something like that. So this is 0.6. That's 0.8. So if I put it in between, but a little bit closer to 0.8, that should get us about 7.3, something like that. 0.73. Yeah, it looks good. 0.73 magnitudes right here. Now, if I look where that crosses the line, remember we're looking at the line. Now, this is closer to 14.2. Notice it's a little closer to 14.3, but that's more like 14.2. Let's go with 14.2. Okay? What that means is, if the Delta Cephei were located in the small Magellanic Cloud, its magnitude would be 14.2. Now, our goal was to find the ratio of brightnesses. And as you can see, if we come back to the formula we had before, B2 over B1, we can write as a function of the two magnitudes. So I'm going to copy this over on the other page, and then we'll start filling it in. Okay, this is the formula as I copied it over. As I use the most logical form, which is B2 over B1 is 1 over 100 to the difference in magnitudes divided by 5, because recall, for every 5 magnitudes we have a difference. For a difference in 5 magnitudes we have a ratio of 100. So, in our case here, we need to be clear which one is which. So, since this asks for the ratio of Delta Cephei to a corresponding star in the small Magellanic Cloud, we should make this one the real Delta Cephei, and that one to be if it were in the small Magellanic Cloud. So that's got to equal 1 divided by 100 to the, now let's see, 2 was the real one, so that had a magnitude of 3.48. And if it were in the small Magellanic Cloud, it would have had a magnitude of 14.2. And for every factor of 100, we have a difference in 5. So I'm going to divide that by 5. And then I'm going to say that equals, and I'll simplify it, 1 divided by 100 to the, and I'm going to subtract these two and divide by 5. Notice I'm going to get a negative number because that's smaller than that. So let's try that. Clear, I'm going to say 3.48 minus 14.2, I hit equals, and then I'm going to divide that by 5, and I'm going to get negative 2.144. And for convenience, I'm going to stick it in memory. So now I can write down right here negative 2.144. Now, what's nice about negatives exponents is that it's the same thing as a reciprocal. So 1 over 100 to the negative something is the same thing as just 100 to that something. So we can write b2 over b1 equals, now notice everything is like a sentence. There's a subject, there's a verb, and there's a predicate. So the subject here is the same as we had here, b2 over b1, which is what we're interested in for this problem. And it's going to be equal to 1 divided by 100 to the negative 2.144. And that's going to be equal to 100 to the 2.144 power. So that's going to be equal to, well, let's pick up our calculator. So I'm going to clear, I'm going to say 100, I'm going to hit x to the y, and then I'm going to put in my well, I got a 2.144 equals. And what do I get? I get 19408.8. Okay. And I'm only given this to 3 significant digits the most, really 2 from what we read. So I'm just going to chop it off right here. I'm going to say 19000 because this 4 is less than 5. So my final answer is the real Delta Cephei is 19,000 times brighter than it would be if it were in the small Magellanic Cloud. Now notice something else. If we look back at her plots, there is some scatter. And so some individual ones are above or below this line. So maybe it could have been anywhere somewhere in here. So that will add to some error. But we're just picking the most likely value on the line. So that is how you find the brightness ratio from magnitudes of 2 different objects.